Our next presenter is Slobodan Simonovic from the Department of Civil and Environmental Engineering at Western University. Slobodan has made seminal contributions to the development of systems engineering approaches to the planning, designing, and managing of complex water resources systems in the search for sustainable and robust physical and societal solutions based on stakeholders' value systems and ethical principles. He has used multiple approaches for addressing subjective and objective uncertainties in managing water resources system.
Good morning, everyone. I'll be talking about managing water resources under global change this morning. And this is basically part of my personal story. The personal story will indicate and present a couple of interesting research concepts that I'm applying to almost every project I have. I'll try to use the rest of the time to illustrate the results of the research with a number of examples. The story started in 1974 and is obviously brought me to today. It was a lot of fun and hard work and sharing knowledge and experience with my students, collaborators, publishing our work and making it available to various professionals interested in field of water resources management. Would like to bring to your attention this interesting publication that my laboratory is publishing, water resources research reports, which last week reached 100,000 downloads with a coverage, world coverage as indicated on this map. In doing my research, focus is now on global change. Global change that includes population growth and migrations, change in the land use with special focus on urbanization, change in our climate. And all these globally changing conditions are affecting infrastructure, hard and soft infrastructure, hard infrastructure in the sense of necessary elements that carry water, energy, transport, goods, and allow communications, to soft infrastructure, which is focusing on the institutional arrangement, social, even some cultural aspects. Focusing on this kind of global change is definitely introducing or imposing on researchers two very significant requirements. One is complexity of the problems and systems we are dealing with, and another aspect is uncertainty in our knowledge, information available, and so on. So the research philosophy that I am following is basically trying to respond to these two important requirements. In addressing complexity, I'm implementing systems approach, where I'm looking at the water resources management problems as social problems with four subsystems very closely interrelated, subsystems of individuals, organizations, societies, and all of them embedded in the environment. All these four subsystems are connected by flows of resources and information, and that kind of provides us with insight in the state of the system and also dynamics of their change. The second part of the research philosophy that I'm implementing is trying to address uncertainty that I mentioned as the second requirement. Traditionally, we were doing that through kind of risk management and introduction of risk into decision-making, water resources decision-making. Risk, as the upper part of this slide is showing, is a static measure. For example, different shades of red are illustrating here the risk of climate change caused flooding for the city of London under one of the potential climate scenarios. Useful information However, information that's not sufficiently giving us the kind of response of the system like city, a complex system like city, to every element of the hazard or disturbance being introduced by, let's say, in this particular case, flooding. So that leads to introduction of quantitative resilience that my research is following, where we are transferring the static measure into dynamic representation of the response of the system to a disturbing condition. From looking at this diagram, we can now actually find out much more about how fast the system is losing performance, what will be the minimum level of performance, and how fast the system can recover. So both risk and resilience together, I think, are my response to that kind of uncertainty challenge being imposed by looking at globally changing conditions. I would like to quote George Box, English statistician, who said, "All models are wrong, but some are useful." And I am ready to accept in front of you that all my models are wrong. They're wrong because I'm using simplified ways of representing the really complex physical and social system. The structure and functioning of the structure is subject to, multiple simplifications. However, these simple simplifications are leading and sometimes resulting in a relatively complex behavior of the system. And that's why I would say that some of these models are useful, useful to building the kind of relationship or path between that structural simplicity and the resulting behavior, resulting complex behavior that can lead to resilience. Let me illustrate the work with number of examples. Some of them are older, as you can see, and I selected these 4 or 5 examples based on, I think, importance that my research did generate over the time. One that you see on the screen is improvement in basically algorithm for improving the hydropower optimization of the Manitoba Hydro, the work from 1990s, where the focus of this interconnected utility was to maximize the interruptible energy export and final storage in Lake Winnipeg, while minimizing the production costs of satisfying the demand for electrical energy. Being interconnected utility and having a large natural storage in the lake, Manitoba Hydro is able to find the optimal strategy how to generate power, export and import it to neighboring provinces and United States in an optimal way. This particular model has been developed, accepted by Manitoba Hydro, and implemented in their practice. The second example I selected is integrated system dynamic model of global change, where we, over the long period of time, worked in developing a relatively complex model structure, as you can see now, connecting approximately 11 sectors, where the population, economy, socio-economical, as well as the kind of physical food production, carbon, climate, are linked to water resources through the kind of demand, quantity, and quality, and capturing the interactions of such a complex functioning system in order to answer what are the best policy options we have in order to address this global changing conditions. One more example is linking and implementing basically the concept of quantitative resilience in adaptation to changing conditions. We have a tool that responds and shows and utilizes the quantitative resilience as a criteria for making decision what are the best adaptation options to, let's say, flood hitting one of the urban environments, and how to respond to that. The last example I have selected, is a computerized tool for developing extreme precipitation and introducing the climate change in that process. This particular tool has been in public use for a period of time, and it's developed for Canada. It can offer at different locations the values for extreme precipitation. Over 3,000 professionals are using it today. And that kind of brings me to the today. What you see on the screen is the kind of graphics generated by my university, indicating that this fellowship in the Royal Society of Canada puts me among the Canada's elite, and I'm very humbled and honored. Thank you very much.